It's L'Hopital's rule. It deals with limits. It says anytime you have the limit as x approaches a of some function over another function, and it was if that limit evaluates to 0 over 0 or infinity over infinity, then what you can do is you can say that that will equal the limit as x approaches a of the derivative of the numerator over the derivative of the denominator, provided that it exists.
How would you know if it equals 0 or infinity over infinity?
You just plug it in.
What would you plug in? Oh, just plug in.
Plug in A.
Oh,
Plug in
okay.
A. Yeah. So if you evaluate the limit and you end up with a 0 over 0 case or an infinity over infinity case, then you do what we've always wanted to do with the quotient rule, but it was always, you know, you're always told no. You take the derivative of the numerator, you take the derivative of the denominator. But this is a limit problem. It's not really a derivative problem per se.
That's only if it equals 0 over 0.
Yes, great question, because we're going to see several problems today that are not going to be 0 over 0 or infinity over infinity, but some other thing like 1 to the infinity or infinity minus infinity, and we're not going to be able to do that.
So is that just the answer then if it's not?
Unfortunately, no, because our goal is to try to figure the sucker out. And the trick at that point is to use some algebra techniques to be able to manipulate it so that it looks like a 0 over 0 or infinity over infinity case, then apply L'Hopital's rule, then we can get an answer. So a lot of the stuff that I'm going to try to be kind of directing y'all today is on those algebra techniques. Okay? But yeah, great questions here. Got to go with the 0 over 0 and infinity over infinity. Okay. Let's go ahead and look at one of these. Let's go ahead and look at maybe number 15. So that says the limit as x approaches infinity of 2x over ln x. Let's talk about the numerator. As x approaches infinity, as x gets larger and larger, what does 2x approach? Class? It approaches infinity. What about the denominator, ln x? James? Do you remember what the graph of ln x looks like?
No.
Alright. Or quick reminder, it looks something like this, where it looks like a sideways exponential. And as x gets larger and larger and larger, the graph of ln x does get larger indeed, though very slowly, but it does continue to increase without bound. It is not asymptotic. Okay? It doesn't approach a specific horizontal value or y value. So this is an infinity over infinity situation. So now let's take the derivative. What's the derivative of 2x? Anyone?
2.
And the derivative of ln x?
1 over x.
1 over x. So we can write that as, instead of saying 2 divided by 1 over x, we can say 2 times the reciprocal of the denominator. So the reciprocal of the denominator is x over 1. So we have the limit as x approaches infinity of 2 times x. So if we want to write that all out, the limit as x approaches infinity of 2x. What's the limit as x approaches infinity of 2x? Anybody?
Infinity.
It's infinity. Can't simplify that at all. So there, so since this limit equals infinity, this limit right up here also equals infinity by L'Hopital's rule. Okay. Let's look at another one, maybe number 17. This is the limit as x approaches pi over 2 of 4 secant x minus 4 tangent x. I don't know about you, but I particularly don't like dealing with secant and cosecant and things like that. I prefer sines and cosines. So maybe let's just turn that secant into a sine or cosine. What would we turn that secant into?
1 over cosine.
1 over cosine. Hey, you know what? While we're at it, let's go ahead and turn that tangent into sines and cosines.
Sine over cosine.
Yeah, sine over cosine. Well, when I do that, that problem actually turns into we've got fractions here, we've got a common denominator, so let's just go ahead and say 4 minus 4 sine x all over cosine x. Alright, well I take attendance on geometry graph sine x off to the side and graph cosine x off to the side and see if, without a calculator, you can evaluate sine and cosine at pi over 2. Let's go through that. What's up when you graph the sine and cosine then? Alright, so that should come back to mind. Just quick review. Where does sine end? Like, what's that x value? What's its period like?
2 pi.
2 pi? So what's the value right here in the middle?
Pi.
Pi. So then half of that is pi over 2. And we've got a value of 1. Cosine ends at the same location, therefore pi is right there in the middle. And then pi over 2 is when we're crossing the x-axis. So plug these values in. Plug in pi over 2. We have 4 minus 4 times 1 divided by 0, which is a 4 minus 4, so 0. That's a 0 over 0 situation. All right. So let's get L'Hopital up on this problem here. Take the derivative of the numerator. Call it out to me here, folks. Say again?
0?
The derivative of the numerator, if the numerator was 0, yes. Like, let me back up. That's not the derivative of the numerator when we evaluate the pi over 2, but rather the derivative of the numerator when it's in. Oh, you were saying, okay, great. So 0 minus and derivative sign. Okay.
Just cosine.
Yep. 4 cosine x. All the negative sign. So I'm gonna say this is the limit as x approaches pi over 2. Negative over negative is positive, so we have 4 cosine x divided by sine x. So let's plug in pi over 2. Cosine pi over 2 is
0.
0. Sine of pi over 2?
1.
1. 4 times 0 over 1 equals?
0.
0. So this limit equals 0, Therefore, this original limit problem equals 0 by L'Hopital's rule. Number 18 is looking pretty good, actually. That one looks like a different type of problem. The limit of 4x to the x as x approaches 0 from the right. So this one we might need to do just a little bit of thinking here. So this is going to be 4 times, we might need to plug some values in. Like we can try 1 to the 1. Well, that's easy, that's just 4. 4 times 0.5 to the 0.5. Rigel, Harley, figure that one out. James Ivan, let's try 4 times 0.1 to the 0.1. And then whoever finished early, 4 times 0.01 to the 0.01.
For the 0.5 is 2.82. 83.
And then multiply that by 4?
Yes.
Okay, so final answer, sorry, say again?
2.83.
2.83? Okay.
And then the 4 times 0.01,
Mhm.
I got 3.819, so 3.2.
Okay, so that's right here.
3.177.
Okay, we might actually be approaching a number. Might be approaching something like 3.8 something. If we plug in just like straight, we end up like we have a 0. It's 4 times 0 to the 0, but it's basically like a 0 to the 0. See what I'm saying? Because this is approaching 0 and this is approaching 0. 0 to 0, what in the world is that? Not sure, right? Can we just apply L'Hopital's rule? No, because L'Hopital's rule says you have to have a fraction, right? Okay, so let's go ahead and do something. Let's go ahead and I'll show you some of this other technique here. So here's the technique. We say y equals the limit as x approaches 0 to the right of 4x to the x. Now we see that in this expression here, the 4 is not affected by the limit statement, so we'll bring that 4 over outside the limit. So y equals 4 times the limit as x approaches 0 from the right of x dx. Then, if you remember, we did this thing earlier when we had exponents and weird things like that. We took the log of both sides. So, whenever we did logarithmic differentiation, and that's what we're going to do right now. We're going to say natural log of y equals the natural log of 4 times the limit as x approaches 0 of x to the x. And then we'll apply some logarithm properties. Remember, the natural log of something times something else is the natural log of the first thing plus the natural log of the second thing. So natural log of y equals natural log of 4 plus natural log of the limit as x approaches 0 of x to the x. One of the properties of limits that we didn't cover, but it is a property that if you have the natural log of a limit, it's actually the same as if you take the limit of the natural log. Okay? We didn't cover that because we weren't going over logarithm stuff when we did the limit laws. But we can actually apply this natural log statement just to this statement right here and push that in here. So we have the natural log of y equals the natural log of 4 plus the limit as x approaches 0, right? Put that down all the time. Of the natural log of x to the x.
So why can we do that again?
It's a property of natural logs and limits.
Okay.
That you can, it's the same kind of thing where, like, for instance, the 4 is not affected by the log there. It's a little bit more for me to show you, demonstrate this, but you just gonna take my word for it on that.
Okay.
Alright, so at this point, we really let's just focus in on this part right here, okay? So, the limit of x to x. So what we can do here, natural log of x. So I'm just gonna pull this part off and say, let's apply the properties of logarithms here. We can say this is the limit as x approaches 0 of x times ln x. And so then we have, I'm still not at a L'Hopital's rule situation because I have it multiplied. But the way that we dealt with this the other day is we can keep that ln x in the numerator, and then instead of saying multiply by x, we can divide by 1 over x. At this point, we're probably gonna need a extra sheet of paper. This is how we do this thing. All right. So let's tell you what. Let's graph ln x on your calculator, since I feel like we're a little weak on that. James and Ivan, y'all take care of that. Rigel and Harley, y'all graph 1 over x. Come on up here and sketch the graph on my coordinate axis here. Use that green guy.
Okay.
James and I when we all come up here and graph LNX. Yeah, it's actually asymptotic there on the y-axis. So it's asymptotic there on the y-axis. It's asymptotic there on the y-axis. There we go. Alright, looking good. So let's examine these graphs as x approaches 0 from the right. What's happening to ln x? Yep. What value is it approaching there? Negative infinity. And 1 over x as we're getting closer and closer? Positive infinity. So it doesn't matter if you have a plus or minus infinity here, but we have an infinity over infinity situation. Yes, we can finally apply L'Hopital's rule.
So
After all this
to
algebra.
the ln 4.
I'm leaving that's kind of hanging out here.
Okay,
It's in pause
got it.
while we deal with this situation here.
That mess. Alright.
Maybe it'll end up like equaling 0 or something, which would be awesome, and then we're just going to be left with this.
Okay.
But yeah, good question. Okay, so we have an infinity over infinity situation. Finally, let's go ahead and take the derivative. Derivative of ln x is
1 over x.
1 over x. Now, the derivative of 1 over x, oh my gosh, okay. We can do quotient rule, but yuck, who wants to do that? Let's rewrite that 1 over x as x to the negative 1. And what is the derivative of x to the negative 1?
Negative x to the negative 2.
Yeah, negative x to the negative 2, which can be written as negative 1 over x squared. Right, Harley, you see how we did that? Taking the derivative of 1 over x. 1 over x equals x to the negative 1. So taking the derivative of that, pop down, negative, power down, negative 2. And so then rewriting that in fraction form, it's negative 1 over x squared. So that's why I got it written like this. Before we kind of see where all this is going, let's go ahead and simplify this. I'm going to rewrite this as the numerator, 1 over x, times the reciprocal of the denominator, so times negative x squared over 1. So one of those x's in the numerator cancels out with an x in the denominator. And we have the limit as x approaches 0 from the right of negative x. Which is what, Ivan?
0.
It's 0. So, since the limit of this equals 0, we can say by L'Hopital's rule, the limit of ln x of x to the x as x approaches 0 from the right is also 0. That's good news for us. I was kind of hoping that would happen. So now we have natural log of y equals the natural log of 4. Therefore, y equals 4. Don't seem too thrilled about that, James. I'm like super excited, but that's alright. And what was y?
Was the limit of 4x to the
Yeah, that's what we're looking for in the first place. The limit of 4x to the x as x approaches 0 from the right equals 4. Well, look at our table of data. That we are at 2.8, then 3.1, then 3.8. Maybe if we had carried this down a few more times, maybe we would have been getting close enough to 4.
So our answer's 4.
So our answer's 4.
That's a lot of work for.
The answer's not zero.
Well, no, this limit right here was 0,
Okay.
but that wasn't the limit that we were looking for. We were looking for the limit of 4x to the x. This was the limit of ln x to the x. Alright, that's a great problem there. Let's do one of these that looks like it's kind of like an oddball, 36. Especially because the instructions say, evaluate each limit using L'Hopital's rule 1 or more times. Ooh. Limit as x approaches 0 to the right. 5x. Yeah, 36. We're probably going to need another sheet of paper for this one as well. Okay. Now I can already, by looking at this, of the 3 that we've done today, which of those 3 does this one more closely resemble?
To the 4 to the x to the x.
Yeah, it looks like the x to the x. In fact, anytime you're going to have something like an x to the x type situation, you're going to need to do that y equals the right hand side, then take the natural log of one side and the natural log of the other. Okay, that's kind of what you end up having to do in order to hopefully get to a situation where you can have L'Hopital's rule. Yes.
Is it safe to say that any limit that has like a coefficient and then x to the x, it will, like the answer would be only the coefficient?
It's possible. But if this isn't x to the x, this is x to the sine x.
Yeah, I know, but there's like number 5 is 5x to the x.
So I mean, what would be the difference between what we just did and if there was a 5 right there? I mean, instead of a 4, there'd be a 5 right there. Instead of a 4 right there, there'd be a 5. Instead of a 4 right there, there'd be a 5. This right here was totally independent. So yeah,
Okay.
I think that's a safe bet to say. And you can say C work for number 18. The answer to number 5 is 5. Okay, that's pretty good. I like that. Same kind of thing. Seems like it might be applicable to this one, although I don't know if there's any. Are there any other problems that resemble 36?
45.
It's got tangent, yeah. Okay.
And I don't know if 50 counts.
I don't think so because it's a function. Yeah. Okay. So, let's just turn the crank here. So, y equals the limit as x approaches 0 to the right of 5x times sine x. We might as well do 2 things at once. I'm gonna just pull that 5 out front. And then if you remember the last one we did, we took the natural log of both sides. So natural log of y equals natural log of 5 times the limit as x approaches 0 from the right of x sine x. So natural log of y equals natural log of 5 plus the natural log of the limit as x approaches 0 to the right of x sine x. So natural log of y equals natural log of 5 plus, this is going to be the same kind of thing that we saw with the previous problem. The natural log of the limit is equal to the limit of the natural log. And so I'm just going to focus in on this part right here. The natural log of anything to a power is equal to that power times the natural log of the base. So this is going to be the limit as x approaches 0 from the right of sine x times ln x. Alright, unfortunately we still don't have a L'Hopital's rule type situation. So we're going to need to shove one of these in the denominator and put it as 1 over that thing. Which would you rather shove in the denominator, the sine or the ln x?
The sine.
Okay, so the sine, alright. So this is going to be 1 over sine, and then we still have ln x. We know from last time that ln x looks like this. The graph of 1 over sine.
It's a cosecant.
It's cosecant. Now remember the way that we kind of did the cosecants when we were in pre-cal, is we said that every time that you cross the x-axis, it's going to be 1 over that number, so we had asymptotes. And at the peak of this looked like, sort of like a parabola type thing opening up in the trough there. It was like a parabola opening downward. But this blue is enough to kind of see that as x approaches 0 from the right, this is approaching infinity. And same thing over here, ln x is approaching negative infinity. So that's good for us. So we have an infinity over infinity situation. That means we can try to apply L'Hopital's rule here. So derivative of ln x is
1 over x.
1 over x. And maybe we should, you know, 1 over sine. We said that was cosecant.
Mm-hmm.
What's the derivative of cosecant?
Was negative cotangent?
Not quite.
See derivative of cosecant? Negative cosecant times cotangent.
Yep. So the limit as x approaches 0 from the right. One of the things that we need to do, if possible, now they already told us that, I think, didn't they, that this is evaluate using L'Hopital's rule 1 or more times.
Mm-hmm.
Yeah, we're going to have to do L'Hopital's rule again. Before we do that, we want to simplify this as much as possible, okay? So that 1 over x, I can actually write that as x in the denominator, okay? And then, if you remember, cosecant here in the numerator can be written as sine in the numerator and cotangent in the denominator can be written as tangent in the numerator. Okay? So if we think about what happens as x approaches, gets closer and closer to 0, well, the denominator clearly approaches 0. And the numerator, sine x, we saw that that's going to approach 0. So it's going to be 0 times something, who cares what it is, so it's a 0. We have a 0 over 0 situation. So we get to apply L'Hopital's rule again, which means take the derivative of the numerator and the derivative of the denominator. James, make sure. Am I still good here?
Mm-hmm.
All right. So let's do all this in one shot here. X approaches 0 from the right. We have negative. So the derivative of sine times tangent, we're going to have to do product rule. So the first, sine, times the derivative of the second. The derivative of tangent is?
Secant squared.
Okay. Secant squared x. Plus the derivative of the second, so tangent, times the derivative of the first. Derivative of sine is cosine. All over. The derivative of the denominator is just going to be 1. So, we now have the limit as x approaches 0 from the right of negative sine x. Secant squared, we can write that as cosine squared x in the denominator. I'll distribute that minus. Minus tangent divided by cosine. Let's go ahead and plug 0 in and see what we get. What's the sine of 0?
0.
0. Cosine of 0?
1.
1. Tangent of 0?
0.
Cosine of 0? 1. So we have, so just doing direct substitution, we end up with 0 minus 0. Are you telling me this whole thing equals 0? That this limit equals 0? Which means that this limit equals 0? Which means that we have ln y equals ln 5? And therefore, y equals 5, and y was equal to the original thing. So we have, what, are you serious? I don't know about y'all, but I was getting real worried when I saw this sucker. I was like, whoa, that's gonna cause some problems. But it didn't. It actually did direct substitution and canceled each other out. That's nice. So we applied L'Hopital's rule once, then we applied right here, and then we applied L'Hopital's rule again. Alright, here's ones I want you to do for homework. I want you to do number 7, because that's got a 1 over the exponent, which we did not talk about.
Mhm.
I want you to do number 8. Because you're gonna have to combine those terms into one fraction. Number 10. Number 16. And number 25. There's a whole lot of other problems on this one, but I don't really feel like we need to do all of them. So 7, 8, 10, 16, 25. This we do on Wednesday. And for homework tonight, in preparation, you need to read through 4-9 and read and take notes. Have those notes ready tomorrow in class. So notes on 4-9, antiderivatives. So the rest of these problems, they're nice and fun. I'm not gonna assign the rest of them, just the ones that I told you right there. That homework set was, I just pretty much had the worksheet generate every single problem that it possibly could. So it's kind of like a question bank. It's easy for me that way. Alright, today we talked about applying L'Hopital's rule, looked at lots of examples, did that little natural log trick. And I think we'll be good. James, go ahead and kill it.